Hi guys, it's been a while since I put up a video, so I guess it's time. I've been doing some stuff around here, primarily Arduino computer type stuff as it applies to the shop, and got something ready to show. Got the electronics hardware and the software pretty much done. I have yet to machine the case or wire it up. So what I can show you is what I have on the bench and how it works with the oscilloscope, and then we'll get into machining the case, and then I'll show you how it works. Hopefully it will work, because I haven't hooked it up to the welder yet, so we're going to see what happens here. This is my best shot, and I'll show you how I went about designing the hardware and the software. So let me show you my welder. This is my Miller Synchrowave 180 SD, which is a square wave TIG and stick welder. And when it's in TIG mode, well, actually when it's in stick mode too, but you don't do it. When it's in TIG mode, the pedal goes right there. So what I decided to do, after watching some of Jody's videos where he talks about these inverter welders, I decided that I could do a little bit by intercepting the signals that go to the pedal, so that I could pulse it and change the frequency and all that. Things that you would normally do by just stepping on the pedal and modulating the current. I'm going to have in a little computer. So that's the target, or should I say the victim of this latest experiment. And when next you see me, I will be showing you the hardware. Stand by. Okay, so let me show you what I've got here. A nice die-cast box, so that when I throw this thing all over the welding table, it won't get all hacked up. And also provides nice EMI protection. That would be protection from the weld EMI getting into my electronics. So we got some connector parts, some pins. Now here's the connector set that I worked out, was for the Miller welder and pedal. And I'll tell you what those numbers are later, just in case you're interested in this. If you broke your connector and you want a new one, or you want to build this thing. And female pins. That's a cable gland, because what's going to happen is this connector is going to be on this side, which will go to the pedal. Well, let me be a little more clear with this. This connector is on this side, and the pedal plugs into it. Then I have a cable gland that's going to hard mount to this box, have like a short pigtail with this on it, which will plug into the welder. Alright, some other little goodies in here. Got a DC to DC converter to convert the 12 volts that comes out of the the 24 volts that comes out of the welder to 12 volts, which is what my circuit needs to work. And later on, I think this is going to be a two-part video. The first part will be what we're doing and all that, and the second part will be machining this out and then trying it out. I may even go to 3 parts if it runs too long, but anyways, let me get this set up. I've got a demo mode on this software, which will allow me to mimic the pedal, and then I've got the 3 controls for the frequency, the depth, and the total amperage. So let me get it set up on the scope, and I'll show you what's going on here. Hang on. Okay, so what I've got here is my Nano mounted to a proto board, and I've got some of the pots on here are simulating pots. Like this one here simulates the welder knob, and this one here is the pedal. Oh, you can't see that, can you? Okay, so that's the pedal. Then I have frequency, percent of the low end. I just call it percent, and the duty cycle. So basically what happens here is this proto board has an amplifier on it, so I can generate the 10 volt signal that the welder needs. The welder supplies a 24 volt bus out to the pedal, so I have DC to DC converter to make that 12 volts, and then this board runs off of 12. So anyway, what we've got here is frequency, duty cycle, a percentage, which I'll show you on the scope what that means, and then what the weld amps, maximum weld amps can be. So let me reposition the camera here and show you the scope and show you what I'm doing. Okay, so basically this is 0 volts here. This will be 10 volts up here. What I can do, I'll show you first of all a 50% waveform at 100 hertz. So if I step on the pedal, this is what the weld signal looks like. Now I have control over it with the this is the pedal. So down here it's like I'm not stepping on the pedal, and here I'm wailing on it full blast. So you can see what happens here is that percentage is, I got it set to 10%, so that's 10% of the maximum current I'm commanding. So I'm commanding 180 amps. So this is 18 amps here. If I command 50 amps, this will be 5 amps. Okay. So let me now what the other mode that this thing can go in is if put the frequency down to 0, then it goes into a pass-through mode here. What that does is it just follows the pedal. This would be like if I didn't have this circuit in here at all. You know, if I step on the pedal, I command the amps. So this thing will go up to 150 hertz. And let me just set a nominal here of, say, 75% on the duty. So what this is showing is I'm commanding, I still got pedal command here, but you can see the frequency is now a lot faster. It's 150 hertz, and the duty cycle has changed from 50% to 75%. So that's basically how this works. This would look like, you know, if I was stomping on the pedal at 150 times a minute, or a second rather. And you know, for those really special jobs, I can set it down low, like say to 1 hertz, and then
So that'd be pulsing along, off, on, off, on, off, on. The only thing I can't do with this is AC balance, because obviously this thing's driving the pedal and you need an inverter to do AC balance. I can't switch my welder that fast from positive to negative. So that's basically the functionality of this board. And I can show you the code. So hang on, we'll show you how this thing actually works. Okay, so here we have our Visual Studio here, and we'll get the software up for the pulser. So let's do some stuff here. So the first thing I do is I comment on all my I/O and how it works. The welder wants to see 0 to 10 volts for 0 to 180 amps. Arduino's on 5 volts, so take the 10 volt signal on the inputs and divide it by 2 with a resistive divider and some clamps and make it a 0 to 5 volt signal. And on the output I take my 0 to 5 volt PWM, filter it, put it through an op amp with a gain of 2 so that I generate a 0 to 10 volt analog signal at the output. So this is how I talk to the LCD. It's a serial LCD. It's one of those serial backpack things from Adafruit. Here's my hardware pin stuff. Some constants. Basically, I made this kind of generic. I could have hard coded this for an SD180, but I figured if somebody else wanted to use it, you could go in here and change all this stuff to do what they wanted to do. This is kind of interesting right here. Anything below 5 counts on the frequency pot, and I assume that you're trying to set a 0 frequency or DC, and so I put this thing into pass-through mode, which I'll show you later. Okay, some storage for some memory. I got a flag. I got some values for the pot counts and things, and then I got some long stuff for the timers and other math that needs to be done. Notice I'm not doing any floating point in this thing at all. Okay, so setup routines, you know, pretty routine stuff. Set some pin modes. This here, I want to get the carrier frequency up as high as I can so I can minimize my filter and my ripple and stuff on the output. So I crank it up to 32 kilohertz. Right now I'm doing the change interrupt on the contactor for the interrupt service routine. I may change this to level sensing if I have noise problems, but we'll just have to see what happens. Okay, and then we talk to the LCD at 9600 baud. We set up the display, rows and columns, contrast, backlight values, colors, cursors off, clear the screen, home it, print a splash screen. Pretty straightforward stuff there. Okay, so the main loop has two, what do you want to call them, branches that it goes through. What it does is some preliminary stuff here to determine what mode it's in. Basically, it's the bypass flag. So if bypass flag is set, that means, or if it's cleared, that means that we turn the backlight green, which means it's ready to, you know, set up. You can turn the pots and set the values and things like that. If it's in bypass mode, sets the backlight to blue, which, oh, I don't need this here. Work in progress. Okay, so if it's in bypass mode, it sets the backlight to blue, and you know, green means it's ready to pulse, and blue means it's ready to pass through. Red means it's actually welding. Okay, this has to do with displaying the the dead zone of 5 counts. If it goes below 5 counts, I set it to 0, and that's so it doesn't like bounce in and out of that mode with the noise. If it's not in bypass mode, I just map the frequency the normal way, scaled correctly. Okay, this is how I generate the waveform. I'm not generating it with a pulse width modulated signal, with a pulse width out of a digital pulse width. I'm using the analog write command to write various values out to the pulse width, which is essentially a DAC, if you want to look at it that way. So this is the pulse width high, and this is the value for it. This is the pulse width low, and this is the value for it. So when it's high, it's putting out pedal amps, and when it's low, it's putting out a percentage of that, which I'll go into later. Okay, here's the branch right here, and if the pedal is not pressed, this code runs, and if the pedal is pressed, this code runs right here. So if it's not pressed, if I'm not welding, then I can set all the pots and frequencies and things like that. So this is where I read them. If it's in bypass mode, I don't need to read any of the other ones, so I don't, but I do need the frequency pot to tell me I'm in bypass mode, and then I also need the amplitudes. So again, if we're not welding, I read the pots, I calculate out the timing. That's all I need to know right now. I don't calculate the amplitudes. And then I display those values of the pots on the display. And that just loops through here. If I do start welding, then this part of it runs. And this is where I calculate the amplitudes. So what I do here is I read the pedal amps, and I read the welder amps up here, right here. Well, max amps tells me what the welder knob on the SD180 is set to. So I use that right here. I scale them from 0 to 1023, which is the full range of the A to D converter. I scale it to 100%. So what I'm doing is I'm scaling the pedal to 100% and the welder setting to 100%. So that tells me, all I need to know about those two knobs. I calculate the value for the pulse width high, the current value for pulse width high, by multiplying those two together, which was like a gain function. Then I multiply it times the welder amps, and then I divide it out. This is just to make the math work right, because I'm not doing float math, I'm doing integer math here. So I compute the current value for the pulse width high here, and then I map it so that I can get it to drive the output of the pulse width. The output of the digital write, or the analog write command, is from 0 to 255, so I scale this to that. And then I calculate the current for the low value based on the percent and the value of the high value. So that gives me the 4 things that I need: the 2 pulse widths, the pulse high, the pulse low. the value high and the value low. This is a state machine here, and what it does is it goes based on the frequency that I selected. Pulse width high and pulse width low are the period for the whole thing. So what I can do here is I can say, okay, I start at t equals 0, okay, and then at t equals 0 plus pulse width high, I switch to pulse width low, and at t equals 0 plus pulse width high plus pulse width low, I reset. Here's the actual commands that write out to the D to A. Can call it a DAC. It's pulse width modulator with a filter on it. So this is where I write it out, and at the next iteration up here I write out the low, and at the next iteration here I reset everything and start for the next time. So that's how the state machine works, and that's how I generate the waveform. What the hell is this thing doing? It's supposed to close it. Alright. Strange. Alright, anyways, here's the interrupt service routine that it basically gets executed whenever the pedal contactor changes state. And what I do is I set the value of contactor state based on whether it's low or not. And if it's high, which means I took my foot off the pedal, I always default by setting the command amps to 0 at the welder. Now it's not necessary for my welder. If I open the contactor, it ignores this, but some welders may not like a command voltage on the input and having the contactor open, so I always write it just in case. If the contactor state goes to 0, this is where I get the start time for the waveform. If I'm in bypass mode, then I set the backlight to blue here. If I'm in bypass mode and the contactor is not energized, I set it to blue. If the contactor is energized, no matter what, it's always red. The backlight is always red. And if it's not in bypass mode and the contactor is not pressed, then it's in the setting mode where I set the thing to green. These are display routines. I have two of them. One of them displays the headers, frequency, duty, cycle, max, and percent that you've seen on the LCD. And then this one here displays the actual values that go into those places. Duty cycle and percent are 2-digit numbers all the time, so I never have to erase them, so I can just write new values in there. But frequency and the welder amps can be 1, 2, or 3 digits, so I have to go in and erase those from the previous values, because if I had a 3-digit value there and it went to a 2, you'd have garbage in there. So that's what that does. Force flag forces the routine to print the values no matter what. If I don't have force flag set, then it doesn't, when this routine executes, it won't print the value unless it's changed. So what force flag does is, like, say for example, if I'm coming out of bypass mode by turning the frequency pot up, if I didn't have a force flag here, then none of these values would update. So until one of them changed, or I had to move the pot. So what this does is when it comes out of bypass mode, it just forces an update to this. One of the things I found is when you are writing to the LCD, you never want to allow an interrupt to occur. So that's why I detach the interrupt and then reattach it for this display routine. For the reason that that happens is if this thing's in the middle of a write sequence to the LCD. This is a library which uses bit banging to software serial. If I'm in the middle of bit banging something out and I get an interrupt on the contactor pin, it will corrupt the LCD and have garbage all over the thing. So, you know, this routine is relatively short. I don't even think the operator is going to notice when he steps on the pedal that it's a couple of milliseconds later that things start happening. But if I don't have this, if I allow this interrupt to occur, it's guaranteed to clobber one of these write cycles. Or, you know, it happens a lot. So that's what that's there for. So that's it. That's how the code works. And now we get the fun of making it connect to the welder. See you in a few.